Good day, learners. Welcome to Technical Sciences lesson. My name is Zamisi Lemdima. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. So today we're looking at paper 2 revision, and specifically we're going to be focusing on thermodynamics. Okay, so you're going to be exploring the questions that are mostly or frequently asked in the past question papers. Okay, so you're going to be looking at them in terms of the multiple choice questions as well as the long questions. But before we get into that, we're going to brush off our presentation or our lesson on the things that you and I spoke about when we dealt with thermodynamics in detail, okay? So that we just remind each other what are the terms that are appropriate, what are the calculation that we should know as we're going to be entering in our exam. Okay, so first up, this is our main focus for today. We're going to be looking at thermodynamics like we've mentioned, and then we're going to be looking at prior knowledge that we need to know for us to be able to understand the thermodynamics in detail. We're going to be looking and exploring first law of thermodynamics as well as the second law of thermodynamics. Okay, we're going to be looking at the type of systems that they are, okay, so that we are able to identify them in any situation or scenario that is presented to us, so we can be able to identify, okay, this is the isolated system, this is the closed system, and so on. All right, so we're also going to be looking at the efficient heat engines, okay, their application to our daily lives, and also how the refrigerators work, okay, the science behind having refrigerators and doing what they do, which is to cool, okay, most of our liquids and keep most of our foods in proper conditions. Okay, so our main objectives for today, by the end of this lesson, I want you and I to be able to understand the first and second law of thermodynamics, also to apply it, because application is very important, to see where can we apply the first law and where is second law applicable. Okay, secondly, we're going to be able to understand the concept of efficient engines. Okay, we want us to be able to understand the three types of system that exist and be able to differentiate between them. All right, and also want you and I to be able to understand how refrigerators that is operate. Okay, also lastly, to be able to solve problems involving thermodynamics and using appropriate formula, and be able to select the appropriate formula for a different problem, okay, depending on what the problem is, and then we are able to provide a solution that comes. All right, so by now, from grade 10 content, we should know that matter can exist in three phases: that is solid, that is liquid, as also gases. Okay, so all the matter that there is whether in all this type of phases, whether be it is solids, it is liquids, or it is gases, just know that matter are continuously in a state of what? Of movement. That means that the particles that up that specific matter are in a continuous what? State of movement. All right, so the type of movement of these particles depend on the state of the matter. Okay, whether it be solid, so there will be a limited movement. If it's liquid, there will be more movement as compared to solids, and then in gases there is free movement of these particles that makes up that particular matter. Okay, now the other factor that affects the movement of the particles is temperature. All right, be it that when we put into a cup of, maybe you put your hot water in a cup, and then you put your cold water in a cup, and then you drop tea bags on both of these containers, what you'll see is that in a hot, or rather boiled water, okay, that you've put in one cup, that the tea bag is going to be able to diffuse faster as compared to in what? As compared to in that cold, or rather cool cup of what? Of water. Okay, so what does this tell us then? It tells us that the temperature then acts as a catalyst in being able to allow the tea bag to to dissociate and to diffuse nicely in that part of water. So that is why we say the difference between a cup of hot tea and a cool cup of tea lies in the movement of the particles. So what happens is that in the hot water, the particles of that make up the tea bag are able to diffuse faster in what? In a hot water as compared to the what? To the cold, or rather cool cup of water. Okay. Now, the molecular particles in a cup of hot tea vibrate faster. There's faster movement of these particles than the molecules in a cup of cool tea. Okay. Now, when an object are in motion, we say that they have more kinetic energy. So that was what happens when the tea bag is being diffused in a hot cup of water. Okay. So the particles have got what? The kinetic energy. Remember kinetic energy from grade 10. It is an energy that an object has due to what? Due to its motion. So there is that constant motion in those particles. And when they are so they're going to say when the object is in motion, we say that they have more kinetic energy, and when they are still, they said that they possess what? Potential energy. Just to remind us a little bit what potential energy is. Potential energy is the energy that an object has due to its position above the surface of the earth. So when I put my pen on top of this table, okay, has got more energy as compared to when I put it down onto the floor. Why? Because now there's a certain height in which this pen is on top of. So it's an energy that an object has due to its position above the surface of the earth. So as you can see over here, so there's this what distance between the top of the table and then the bottom of the table, okay, which is the floor. Now, what is temperature? I want us to be able to separate temperature and heat, okay, and find why are these like commonly mentioned or intertwined in certain scenarios, okay. But first up, we're going to be look at individual terms, temperature as well as heat. All right. So temperature is a measure of the average kinetic energy of a molecular particle that make up a substance. Okay, the average kinetic energy, all right, of a molecular particle that makes up what? A substance. So we're looking at the amount of energy that the particle has, okay, or has been able to absorb. Remember, temperature can be increased or decreased depending on where you put your what? Your object, or maybe your let's talk in terms of water, where you put your water. If you put it in the fridge, it will have lesser temperature. If you put it on top of the stove and you put it on 6, okay, on the highest temperature that there is, then it's going to have a higher temperature. Okay, so that is why in these two instances, in the top of the stove and in the fridge, these are going to have a different average kinetic energy. So on top of the stove, they're going to have a higher average kinetic energy because it's absorbing so much heat from the stove, okay? So it's allowing the particles of that substance to move faster, okay, as compared to when it is put into refrigerator, where it's going to have lower temperature, okay, and then that means that the average kinetic energy is going to be even less. All right. So now, a substance of low temperature, refer to it as being cold, all right, and then a substance of high temperature we refer to be as in a high temperature. It means that it is hot, all right. So what do we then see? What is the relationship between the temperature and the average kinetic energy? Now, temperature is then directly proportional to the average kinetic energy of the particles, meaning that when we increase the temperature, it means that we've increased the average kinetic energy of what? Of the particles that make up that specific matter. All right, so this means that when the temperature increases, also the average kinetic energy of the particles will also do what? They will increase. Okay, so you can say that they are directly proportional. So that is why we end up saying, to conclude, to say that the relationship between the temperature and the average kinetic energy is that they are directly proportional. All right, so then how do we measure temperature? Okay, the SI unit for temperature is Kelvin. All right, the symbol used for temperature is then Kelvin is as T. All right, so now temperature can be used to can be measured using a thermometer. Now, as we know from grade 10, we then have different types of thermometers. It depends on what type of metal we want to measure the temperature of. Okay, so it will be, do you want to measure something that is very hot or something that is very, very cold. Okay, so that is why we'll have different thermometers for different particular reason for that. Okay, so these are the types, or rather the common ones that we have. Okay, so we say we have a mercury thermometer. Okay, so it makes use of the mercury inside it, and then we've got an alcohol thermometer, and then as well we have a thermoelectric thermometer. Right, so mostly because now we just came from a more where we had a pandemic of COVID, we had to be tested for temperature. So I know you've seen one or two of these types of thermometers that are portrayed in here. Okay, whether be it sometimes we use them at the clinics where we have to be checked whether we have fever or not, or whether we're trying to test a certain liquid and we're trying to put it deep inside that liquid so that we can tell what is the temperature, or rather the boiling point, or rather the melting point of that particular meter. All right, so now coming into heat, what is heat and how is it different from temperature, you may ask yourself. Now, heat is the energy that flows from higher temperature object to a lower temperature object. Okay, because of the difference in temperatures. Now, due to the fact that these two objects have got different temperatures, heat is then the energy that will flow from a higher temperature object to a lower temperature object. Okay, so they make a typical example on here on how heat is able to flow from one object to another object. Okay, so but before we even explore on that, we have to know that heat is a form of energy. Okay, that is very important. It is a what? It's a form of energy, and its SI unit is in what? It is in joules. Okay, so we've got object 1 and then we've got object 2. That made us write T1, which is the temperature for the object 1, and then T2 for the object T2 for the object 2. Okay, so at first, because object 1 and object 2 are not physically in contact with one another, they are not interacting with one another. Okay, so object 1 has got its own temperature and object 2 has got its own temperature. All right, so we cannot then say temperature 1 is equal to temperature 2, because these two objects are not physically interacting with one another. Okay, however, now when you look at the figure B, okay, which is this one over here, we just looked at A, whereby it's just two separate, that you have an ice cube and then we get a can of a cola. Okay, so these two are placed at a specific distance apart. Okay, so temperature 1 can never be equals to temperature 2. All right, and then when we look at figure B, then now the can as well as the ice cube are then brought closer to each other. That means that now they are interacting, physically touching one another. That means that the heat is going to be flowing from an object of higher temperature to an object of what? Of lower temperature. Okay, so the heat that is in the can is therefore transferred into the ice, okay, so that it's become cooler and have lower temperature, just like in what? Just like in T2. So remember, this is still your T1 and this is still T2. Okay, physically in contact with one another. What is it that we just observed? What is it that we should learn from those figures? In figure A, soft drinks and ice are just in different temperatures. Okay, therefore I have not reached what we refer to as what? As thermal equilibrium, whereby temperature 1 is equal to temperature 2. Okay, so they have not, or rather they are not in thermal equilibrium. However, in figure B, we find that there is an interaction between the two. Okay, so energy is transferred from the cooler, because now it has what? It is an object with higher temperature, okay, to the one that is lower temperature, is transferred up until they are able to reach a certain equilibrium, meaning that temperature 1 is therefore equals to what? In temperature 2. That means that the cooling, or rather the ice the temperature of the ice is therefore had made the what? The can of a soft drink to be what? To be the same, meaning that the temperature on both sides is going to be the same, which is what we refer to be as what? Thermal equilibrium. So hence that is why, as we're about to approach the festive season, you're gonna see a lot of people having their soft drinks in a cooler box and then putting some ice. This is what they wanna trying to do. So there's going to be transferring of energy from a hotter object, okay, or an object with a higher temperature to the one that has a what? A lower temperature, so that they are able to reach a thermal equilibrium. All right. Now, the heat transfer occurs due to the differences in temperature. So once you have the same temperatures for both objects, so there's not going to be any transferring of heat in between the two substances, okay, or the object. All right. So due to the fact that this object A, has got a different temperature as compared to object B, there has to be a transfer of heat in between the two objects or substances. Okay, so that is why, in fact, since the soft drink and ice are both in contact with their surroundings, such as air and the bench, and the equilibrium of the temperature will be the same for both. All right. So this is what happens when we talk about in terms of the transferring of the heat. All right. So the heat will be transferred from it's an object of higher temperature to the one of what? Lower temperature, which is referred to as hot being transferred to the what? To the cold. All right. So what are the terms that I want us to remember when we talk in terms of thermodynamics that you're going to pick up as you are being asked questions in your exam? Okay, so you're going to be asked in terms of what is thermodynamics as general. Okay, so thermodynamics is a science that deals with heat. Okay, it deals with work, it deals with energy. Okay, and those properties of matter that relate to heat, work, and energy, and is concerned with several properties of what? Of matter. Okay, so that is why we have thermodynamics that exists as a field in science. So it's a science that deals with what? With heat, work, and energy, and the properties of matter that relate to heat, work, and energy, and is concerned with several properties of matter in terms of how that matter will behave should the heat change, should the work change, or should the energy is transferred or absorbed. Okay. Now, in a study of thermodynamics, there is a term that we commonly use, and we say it as what? It is systems. What are systems, you may ask yourself? And it's also used to refer to a gas that is enclosed in a container. So we say, okay, because this one is enclosed in the container, we look at what is happening within it, okay, and we separate it from what is happening on the outside. So within that specific container, we refer to everything that happens in there. Should there be changes inside this container? Okay, then we refer to it as a system, and anything outside it, we refer to it as a what? As a surrounding, because now it is used. A surrounding is a term that is used to describe anything that is outside of the system. Let's make a typical example. You just put your water in a pot, and you put it in a stove, and then you light your stove and put it on 6 so that there is heat that is being transferred from the stove into your pot, okay, that is containing the water. Okay, after some time, that water inside the pot is going to start now boiling. Okay, so what is happening is that the water particles that are contained inside the pot are boiling, meaning that they've changed its phase from being liquid up until they gas, because now there's vapor that is being produced. Okay, so that is whatever that is happening within the pot, inside the pot, that means that is the system. Okay, so what is happening on the outside, okay, is the surrounding. Okay, because now it's anything that is outside of the system. Okay, so it happens that sometimes there are systems that are able to interact. So when this pot is closed, meaning that there's a lid that I've put in. Okay, so even in as much as vapor is being produced, okay, however, it hits the lid and then goes back into the water. Okay, now, however, if I open the lid, all right, that means that as soon as my water starts boiling, the vapor is going to interact with the air or with its surrounding. All right, so there will be an open system as compared to the one where I have got the lid closed on, that we refer to as what? A closed system. Okay. We're going to explore that in detail, just that trying to make you see the difference between the system as well as the surrounding. And then we've got internal energy of thermodynamic system as the sum of the kinetic and potential energies of all the molecules in the system. Okay, so it's just an addition. It's the sum of the kinetic and potential energies of all the molecules in the system. Okay, so that is the internal energy because it's happened within, okay, within that system. All right. So let's look at these type of systems that we keep referring to. Okay, we've got an open system. Okay, and an open system is this type of system where there's an exchange between the matter and energy with its surroundings. Okay, remember that example we made in terms of a pot that is being opened and the water is boiling inside this pot. Okay, so now due to the fact that there is no lid that is covering this pot, okay, there is an exchange between the matter and energy with the surroundings, because now the steam, or rather the vapor, is able to interact with the surroundings. So refer to it as an open system because the system is not closed. It is rather what? Opened. All right. And then number two, a closed system is a system which can exchange energy only, not matter, with the surroundings. Okay, same pot, same amount of water in there, it's boiling, however the lid has closed the pot. Okay, so that means the particles that make up that matter are unable to interact with the surrounding. However, there will be what? The change. There can be an exchange in what? In the energy. Okay, but not the matter particle, or the particles that make up the matter will not be able to interact with what? With its surroundings. And that requires an isolated system. An isolated system is a system which is not influenced by its surroundings. Okay, so it's isolated, it's on its own. Whatever that is happening on the outside does not have an impact on the system or inside, or what is happening inside the system. Okay, what does that mean in simple terms? It means that there is no exchange of heat, there is no exchange of energy with the surrounding. Okay, so it's just isolated, it's on its own there, it's doing its own thing. I usually make a typical example of an isolated system to be what? That of a flask. Okay, so it's just inside the flask, the water is there, and it's not affected by what? By the surrounding. Okay, and then these are the types that we have. Okay, there's an open, as you can see on this one, there is no lid in here. And then we can see this one, there is a lid, okay, but there is an exchange of energy between the system and the surrounding. Why? Because if you leave that liquid, okay, I'm talking about liquid because in this example there's a liquid, okay, so it doesn't have to be a liquid all the time, so it can be in solid, a liquid, or a gas, right? So this particular liquid, okay, placed aside, therefore is able to cool off after some time. Why? Because now there's an exchange between the energy of the surrounding and the energy of within the system. Okay, and then we've got the isolated one. Okay, so after having this container with a certain meter, we wrap it around with something so that we don't allow it to cool down. Remember the flask example I made? Yes, because now it allows it to stay warm for the longest of time, meaning that it is isolated like that. It refuses for its energy that is embedded inside the system to interact with the surroundings. Okay, so that is why you find your water is still very hot even after a day of putting it there. Why? Because it is an isolated system. The energy that the water, the internal energy that existed inside the system, have not been used or being shared with the surroundings. Okay, because now once you start sharing the energy of the system with its surrounding, then it means that the internal energy will be lost, okay, due to this interaction. Okay, the most important things as well that I want you to take note of are the thermodynamic variables. Okay, we've got 3 of them. So the thermal state of thermodynamic system is defined as by its temperature, its pressure, as well as what? Its volume. Okay, so those are the three thermodynamic variables that are very, very important. Okay, so these quantities are called thermodynamic variables. Okay, we also have a working substance, still on the terminology. That is very important. We've got a working substance, which is a substance that is able to absorb the heat from the source, okay, and is able to share that energy, whether you are sharing it with the surrounding or you're just doing mechanical work within it. Okay. Now, without wasting any time, let's look at the first law of thermodynamics. Okay, now the first law of thermodynamics, what does it state and how can we relate it to the everyday life? Now, the first law of thermodynamics states that if the heat, which is the change in Q, given as a change in Q, is given to a system, okay, if the heat energy is given to a system, it is used in two ways. Let's go back to our example of a pot with water placed into the stove. Okay, so this pot that has water, which is the matter, and exists as a liquid, is placed in where? In the stove. That and we close it using a lid. All right, and then we turn on the stove and we put it at 6. All right, so heat is going to be absorbed by the system. Okay, so that is why we say if energy is given to the system, so that means that the stove itself is giving some energy into this pot. All right, so how will the system inside this pot use this this energy that is being given to it? Okay, so it can use it by increasing the internal energy of the system, which is very important to notice. Okay, why are we saying we are increasing? Because as this system is absorbing, okay, the energy from the stove, it is increasing the energy of the water inside it. So hence we say it increases the internal energy of the system. Okay, that is one. Number two, okay, in another way in which this this energy or heat is being used is that it will do work against the external pressure. It can be cold on the outside of this pot, okay, or temperatures could be very, very cold. It's winter time, but because we have placed it in the stove, that is allowing for the energy to be transferred from the stove to the system. So that means that it is doing work that is against any external pressures that it can be existing in that form. So there's a nice a diagrammatic representation that I've put in for you. Okay, so which shows heat transfer and then the internal work that is done doing the work against the what? The external pressures. Okay, externally meaning that whatever that is happening on the surrounding has got no impact in the energy that is being absorbed by the system. Okay. Now, microscopically, what do we see when now there is a transfer of energy? Remember, this transfer of energy, we say it is used in two ways. One, we are increasing the internal energy of the system. Two, doing work against external pressures. All right. So, microscopically, what is it that is happening? We define then the change of the internal energy to be that given by the first law of thermodynamics to be a U, which is the change in what, or rather the internal energy, and then the heat that is absorbed minus the work that is done against the external forces. Okay, and then according to the law of conservation of energy, which is very important and very much applicable in such cases, okay, the heat that is absorbed by the system will increase the temperature of the system. Let's say that again. The heat absorbed by the system, okay, this system, this pot system that we have, then it, as soon as it absorbs, this pot then absorb the heat, is going to increase the temperature of the system. Okay, as it does what? As it increases the temperature of the system, it does what? Increases the internal energy of these particles of this matter within that system. Okay, so it's therefore increasing what? The internal energy Okay, if the heat absorbed by the system is sufficient, then system can also do what? Can also do work. Okay, so this is pretty much the breakdown of the first law of thermodynamics. All right, so mathematically, how can we write this? We say Q is equals to change in U plus what? Plus W, which is for work. Let's just draw it down so that we know what Q stands for, what A change in U stands for, and then W stands for. All right. So where Q is the heat absorbed by the system, okay. AU obviously it is the change, okay, because this delta U is the change in internal energy, and then W is the work done against the external forces. All right. So that's how easy it is. So when the heat is gained by the system, okay, you see, this is the system. It is gaining, okay, some energy, okay. Q is positive. When the heat is gained by the system, Q is positive. However, when the heat is being lost, okay, now this system is losing some energy. Okay, so that means Q has to be what? To be negative. Okay, so that is very much important to note as well. And then also, not only that, when work is done by the system, okay, W is positive because the system itself, okay, is doing some positive work. Okay, so work when is done by the system, okay, so it's doing positive work. Okay, and then when work is done on the system, okay, so something is done onto it, okay, so that means it is doing negative work. All right, and then therefore all the energy, okay, is transferred to the system, is used to change the internal energy and to do work. Okay, because there has to be a reason why this energy is being transferred into the particular system. Okay, it has to do, or rather increase the internal energy of the system and also to do work. All right, so that is why we say this means that the energy is conserved in any thermodynamic processes that exist. Okay, so here's our practical application. Okay, so we've got an individual which takes food in. Okay, this food is therefore there so that we as individuals are able to function properly. We're able to have energy so that we are able to do what? We are able to do work. Okay, and also energy is then therefore excreted in different ways. Okay, as we are busy doing the work, we're therefore utilizing this energy for doing all different types of activities. So what we are ingesting is therefore allowing us to be able to do all the activities that we are able to do all the activities that require energy. Okay, we are also able to do what? To do work. All right, so that is why with figure A we say the first law of thermodynamics is applied in terms of metabolism, because we are ingesting, we are taking in food. Okay, so we're taking in ATP, so heat transferred out of the body, okay, and the work done, okay, which is W, remove the internal energy, because what food does is that it increases the internal energy of our system, okay, through metabolism. Okay, while the intake replaces it. All right, so that is why we say food intake may be considered considered as work done on the body. Okay, same process happens with the plants. Plants convert the part of the radiant heat transfer that they get from the sun. Okay, so that they're able to go through a process we call a photosynthesis. Okay, so that they're able to have their own food. Okay, therefore if they uses the sunlight or the radiant heat transfer, there's a transfer of heat from the sun into the plant. The plants then absorb this energy, okay, and use it to therefore being able to manufacture their own food through the process that we refer to as a photosynthesis. All right, so these are the applications of the first law of thermodynamics. Right, and then now we look at the second law of thermodynamics. Now, the second law of thermodynamics states that when the heat is transformed into work. Now, remember the first one, we're looking at how the transferring of it from the source into the system, and then once it is transferred into the system, that what does it do? It increases the internal energy of the system, and also so that there is work that is done. Okay, so now we're looking at the work aspect of it. So the second law of thermodynamics states that when the heat is transformed into work, okay, there will always be some heat that is lost. So meaning that not 100% of the heat can never be converted to 100% of work. There will be that amount that is going to be lost, that amount of heat that is going to be lost. All right. Also, heat will always move from a higher temperature to a lower temperature. Okay, so that is why we refer to it as heat transfer. Okay, because now heat will be there in an object with a higher temperature, and then we transfer it to an object with what? With lower temperature. Okay, so the second law of thermodynamics basically deals with the efficiency that can be sustained by a heat engine, also the direction of the heat transfer. Okay, so that we understand that a heat will always be transferred from an object with a higher temperature to an object with a lower temperature. All right. Now, with heat engine, what is a heat engine before we even divulge into a lot of things? Now, heat engine is a device that converts heat energy to another form of energy. Okay, so it's taking that heat and it's converting to another form that actual device will able to use it. Okay, so not all the energy is converted. So some that will be lost because not all the energy that is absorbed is going to be converted into 100% work, okay, due to the fact that there will be environmental loss, or rather the loss of energy into the environment during this process. All right, so an efficient heat engine, how can we see that this one works way better, and or how do we then compare the heat engine to say, okay, this one is able to do the conversion of heat energy to another form perfectly as compared to the other ones? Okay, so that is where we talk about the efficiency of it. Okay, how do we see that this heat engine is more efficient as compared to another one? So an efficient heat engine will be the one that absorbs a heat from a hot body source, okay, and convert part of it into work as expected, and rejects the rest into a cold body, okay, which is we refer to it as a heat sink, with a minimum energy that is lost to the environment. So pay attention to the last part. We want the minimum energy to be lost into the environment. We want most of it to be able to be converted, okay, into work, and then most of it to be rejected into the body, or rather a cold body, which is what we refer to as a heat sink. Okay, but the one that is proper, the one that is efficient, is the one that's going to have less minimum, okay, very less energy that is being just lost doing no work, okay, or rather not being converted to doing work properly. All right, so efficiency then depend on the difference between the maximum and the minimum temperatures between which engines are operating better at the time. Okay, so that is why we then have a net work done by the system, so that we can tell how much was lost into the environment, how much was being converted, and how much went to the cold body. Okay, so that is how we can then tell, okay, this is a proper heat engine, okay, and this is not so good due to all the three properties that we look at: the ability to be able to convert the heat energy into any other form, also the ability to reject it to the cold body, or look at the impact that it has, or the amount that is then rejected or rather lost into the environment. Okay. Now, the efficiency of the heat engine is therefore defined as the ratio of the heat that is being converted into work to the total heat absorbed. Okay, how much was it that was totally absorbed by the system, and how much was it that was converted to doing work. Okay, so that is why when we calculate the efficiency, we say the heat converted into work divided by the total heat that was absorbed. In this total amount of heat that was absorbed, how much of this percentage was able to be converted into work, and how much then was taken by the environment. Okay, so if the engine does not lose any heat to the environment, so the efficiency, we calculated as saying efficiency is equal to Q1 minus Q2 divided by Q1. Okay, therefore commonly efficiency can be expressed in the form of percentage. That means that we have to times it by 100, as we have seen in this formula in here. Okay, so we want to see in terms of percentage how much exactly, okay, has been converted into work in a whole of this one, of the heat that was absorbed in total. Okay, so let's give a practical application of what we're talking about. So as I say, if an electrical appliance is like a hairdryer, like a shaver, like a computer, like a cell phone, etc., suddenly heats up more than it used to, then has been repaired. Okay, so it has to be repaired because now it is operating at a lower efficiency. Okay, so it can become a fire hazard. Even yourself, you cannot be able to hold it and just dry your hair properly. Okay, so after it just heats up for no good reason, the next thing is that it's just going to stop working totally. Okay, that shows that it is operating at lower efficiency. Okay, this is just a demonstration of how heat is transferred from an object of higher temperature into an object of cooler temperature. So that is why this TH here is standing for the temperature for the hot. Okay, it's a hot object, and then over here it's a temperature for the cold object. Okay, so this is a transfer as it happens. Okay, however, here we're just being shown that as we are absorbing, or there's a transfer of heat from an object of hot, or rather a higher temperature, okay, some is going to be converted. Okay, the heat engines are therefore responsible to use this absorbed one so that they are able to do what? To do work. Okay, that being said, it has to be able to then increase the internal energy and to be able to do work. That what first law of thermodynamics says. All right, and then most of it then is going to be going into a cold body, okay, which we refer to as what? A heat sink. So that is just a detailed rather explanation of what that diagram really shows us. Okay, so A, which is figure A, it's showing just a spontaneous, okay, transfer of heat from a hot object to a cold one, consistently with using the second law of thermodynamics. And then B, it is showing a heat engine presented by what? A circle that uses part of the heat that is transferred to do some work. Okay, also the hot and cold objects are called hot and cold reservoirs, and then QH we refer to as the heat transfer out of the hot reservoir. Okay, and then W is for the work output, and then QC is the heat transfer in the cold reservoir. All right, now the net work done, the total amount of work that is done, okay, by the system equals to the net heat transfer into the system. Okay, why? Because we are unable to do the work without the heat that is being transferred. Now let's look at how then do refrigerators operate. Okay, now while heat engines, the transfer from the heat from the hot to the cold substances in refrigerators. Okay, now in refrigerators what happens is that for example, not only refrigerators, the refrigerators is the heat pumps, it's the air conditioners, it's refrigerators. They all utilize the heat transfer from cold to what? To hot. Okay, which is just vice versa of what we're talking about. So they will need a special heat engine to do that conversion. Okay, so the heat engines, what they do is that they run backwards. It's no longer now from the hot to the cold, but it's from the cold to the what? To the hot. Okay, now heat transfer occurs at a cold reservoir, okay, into the hot one, which is a QC and QH. This requires work input. Okay, it requires for a lot of work to be done by these heat engines, okay, which is also converted into a heat transfer. Okay, so it's still the transfer of heat, but just that it runs backwards. So we require the specified and special heat engines that are going to be able to transfer from the heat from the cold into hot. Okay, so the heat transfer to the hot reservoirs is therefore given as QH is equals to QC plus what? Plus W, because still those heat engines are able to do what? To do work, but just that it is doing work backwards. Okay, so this is just a laydown of how refrigerators work. So you've got your evaporators that are coming in here, okay, and then here is where the transfer of energy is happening, okay, which is what we refer to as what? As heat engines. Okay, so starting from over here, we're going to have your condenser on, and then which is on your valve 1, and then we have your expansion valve, and then you've got your heat engines over here, and then you get your compressor. All of that works so much so that we are working or using the heat engines to transfer from the cold into the hot one. So as you can see here, you've got the cold air that is coming from the surroundings, like the surroundings as the cold air in general. However, we convert it so that the condenser is able to shift this air after having been compressed, so that it's able to shift from the cold air from the surroundings into the hot air. Then the expansion valve is the one that is able to move it from being hot into what? Into being cold, so that the fridges are able to do it. So remember, this is happening from the outside where we get our cold air from, okay? And this is happening on the inside, so that we are able then now to change whatever that is being hot to being what? To being cold inside the refrigerators. Okay. Now, let's apply the knowledge that we've got today in terms of refrigerators, in terms of the heat engines, in terms of the terminologies that we need to know, in terms of thermodynamics, in terms of like the first as well as the second law of thermodynamics. Now let's time to now apply it in terms of the most important SI unit that we should pay attention to. Okay, all of that we've just summarized today. Therefore, now we're going to incorporate and use that knowledge so that we are able to answer our multiple choice questions and also the long type questions. Okay, so the first one is taken from the past question papers, various of them, and then it goes on to say the SI unit for specific heat capacity is the, okay, remember the strategy of being able to answer the multiple choice questions. Explore all the options that are there. Remember, you're going to be given 4 options, okay, but only one is correct. Okay, so amongst all the 4, there are 2 distractors. There is one that is similar to the answer, and there is an answer. All right, so please pay attention to all the options that are provided. All right, so the first one is saying the SI unit for specific heat capacity is, okay, so bear in mind there is a specific heat capacity that is different for any type of matter that exists. So usually they're going to give you a table with specific heat capacity for different type of matter. Okay, for water, for oil, for different of them. So now you have to be able to select what you want at that specific time and then be able to use it in terms of your calculations. So the question is not that right now. The question is which SI unit is for the specific heat capacity. So what is the SI unit? How do we measure the specific heat capacity? Okay, so it's definitely not A, okay, because Kelvin is used to measure temperature. Okay, B, it is this for option B. They're saying it is joules per kilogram Kelvin, which is correct. And then C is joules. No, because for that one, we use, it is for what? For energy. And then joules per kilogram, definitely not that one. Okay, because that one is for heat capacity alone, not specific heat capacity. So the correct answer is B. All right. And then we look at multiple choice question 1.2. It says that the formula that gives the relationship, okay, the relationship between heat capacity and specific heat capacity correctly is, so we've got option A, Q is equals to MC times delta T, okay, and then B, C is equals to M divided by C, or option C, which is saying C is equals to Q divided by change in time, and then D, it is C is equals to MC. All right, so remember we have specific heat capacity and then we've got heat capacity. Definitely not all of them apart from this one. Okay, so option D is the most correct one. And then now this one is more of a definition. Okay, so we have to know how to define what is then a specific heat capacity. Okay, specific heat capacity is it option A, which is the amount of heat required to boil 1 liter of water, okay, 200 degrees Celsius, or B, it's the amount of heat required for the refrigerator to maintain a temperature of -4 degrees Celsius, or is it C, that is the amount of heat required to increase the temperature of a substance of 1 kilogram by 1 degree Celsius, okay, or it is D, the amount of heat required to decrease the temperature of a 1 kilogram substance by 2 degrees every second. Okay, so definitely not all of them, because now a definition is just a definition. So you have to be able to, if you are asked in terms of specific heat capacity, you'll be able to write it in full. Okay, but in this case, they've given us the whole definition in full, just that they want us to be able to point it amongst the 4 given options. Okay, so the correct answer is the amount of heat energy required to increase the temperature of a substance of a 1 kilogram by what? By 1 degrees Celsius. So it is option C. Multiple choice question 1.4. It says, which one of the following combinations contains thermodynamic variables? Okay, which one of these 4 options has all the correct thermodynamic variables? So the option A is the kinetic energy, temperature, and pressure. Problem there is kinetic energy, okay, because kinetic energy is not part of the thermodynamic variables. And then option B, heat, internal energy, and external energy, not so much. Option C, temperature, pressure, volume, everything looks perfect in there. And then heat, energy, and work, no. So the correct answer is C, temperature, pressure, as well as volume. All right. Now let's explore the long questions. Okay, so this is taken as question 6 from past question papers. It says thermodynamics is a branch of technical sciences that is built upon the fundamental laws which heat and work obey. All right, so in our study, we saw that these laws place additional restrictions on the use of energy in the form of heat and work, restrictions that the law of conservation of energy do not imply. All right, so first question is saying, state the law of conservation of heat. Okay, remember, 2 marks is, you get it by stating it nicely in full. Okay, or if you omit certain terms, then you can't get it in full. So it's 2 marks or nothing. Okay, so what is then the law of conservation of heat? What does it state? Okay, it states that the law of conservation of heat states that the amount of heat that is lost is equals to the amount of heat that is gained when heat is lost. Okay, so the amount of heat that is lost is equal to the amount of heat that is gained when no heat is what is lost. Okay, so when no heat is lost, therefore it has to be equal. The amount that I give in should be the amount that I get in return. Okay. Also, moving on to a different question, 6.2, it says 520 kilojoules of heat energy is supplied to a certain machine. Okay, then of that 520 kilojoules, 310 kilojoules of this energy is converted into mechanical work. Okay, calculate the change in internal energy of this machine. All right, so choosing a correct formula is a skill. Okay, that means that you should be able to highlight what is it that is given to you. Okay, so this is the heat energy that is supplied into the machine. Okay, that means this Q is changing what? Changing Q because it is supplied, it is given into the system. Okay, and then 310 kilojoules of energy is converted into mechanical work. That means it's the amount of energy that has gone to do work, specifically mechanical work. And then internal energy, okay, that is change in U. Okay, so this makes it an appropriate question for us, the appropriate formula to choose for this specific problem. All right, so 520 kilojoules, remember energy has to be in joules, so this kilo means 1,000, so this means that this is basically 5,000. Why am I saying 5,000? Why am I saying that? So this means that it's 520,000 joules, and this is going to be 310,000 joules. All right. So let's do our substitution. So that I just did that so that you are able to see where that kilojoule. Why now that we have to change from kilojoules to joule? All right. So 520, this is our substitution, and you get our final answer of change in U, which is our internal energy, which is 210 joules. Okay, or someone else can just say 210 kilojoules, which is perfectly fine. Okay. And then 6.3, we have to define a working substance in technology. Remember, it is a substance that absorbs the energy, okay, or heat in this case, from the source. Okay, what we do with it, you already know. We are increasing the internal energy. We are also doing work against the external forces. 6.4 goes on to say, give 2 examples of a working substance. Okay, what is that substance that absorbs heat energy? Okay, so heat engine, okay, refrigerator or a coolant, and then hair dryer, a lawnmower, and then electrical drill. So all of these are examples of a working substance. Okay, and then we went on to question 7. All right, question 7 deals with specific heat capacity. First question, it says define heat capacity. Okay, remember we had a multiple choice question whereby we had to select an option for a correct definition for a specific heat capacity. What did we say? We're saying it is the amount of heat that is required to increase the temperature of a 1 kilogram of the substance by 1 degrees Celsius. Okay, you state it like that, it's 2 Mach. 2 or nothing. You omit certain terms, you cannot get it as 2 marks. Okay. 7.2, it says distinguish now, differentiate between what is a surrounding and what is a thermodynamic system. Oh, remember what we said about the surrounding. Surrounding is anything outside of the system which has bearing on the behavior on the system. Okay, so should we allow the system to interact with the surrounding, it will have a certain barrier on how the system operates. Okay, and then on the other hand, a thermodynamic system, it is a portion of matter, for example, a gas enclosed inside a cylinder fitted with a piston. Okay. 7.3, they say now, suppose you are given 1 liter of water in a container, and then in another container you've got 1 liter of ethyl of alcohol. All right, so we've got 1 liter container, we've got water in it, and then we've got another 1 liter of container, and then we've got ethyl alcohol. Okay, ethyl of alcohol. Now, 7.3.1, which one of the 1 liter liquids, is it the alcohol one or the water one, can be used as an excellent coolant? Which one can we use to cool down? We want to cool, okay, to get rid of this more heat. Are you going to use alcohol or are you going to use water? Definitely water. Okay, so water is an excellent cooler. And then 7.3.2, explain your answer. Why did we say that 7.3.1 is an excellent coolant? Okay, using specific heat capacities of the 2 liquids. Okay, which one has a highest heat capacity as compared to the 2? Because the one that has got a highest specific heat capacity is the one that is an excellent coolant. Okay, and between those two, the one that is an excellent coolant because of its highest specific heat capacity is water. Okay, so you had to mention that because of its heat, a higher, okay, specific heat capacity, it is an excellent coolant. Okay. Why does that keep popping up? All right, 7.4 says 220 grams of water at 90 degrees Celsius is added to a certain unknown mass of water. So this is an unknown mass of water. Why isn't my pen writing? Okay, it's acting up. And then at 10 degrees Celsius. Now the final temperature of the mixture is 33 degrees Celsius. Okay, and then the question goes on to say, calculate the unknown mass of the water. Okay, so you've got your 220 grams of water at 90 degrees Celsius that is being added to another unknown mass of water. So the second mass is unknown, but we know that its temperature is 10 degrees Celsius. Now we have to find the mass of this unknown water. Okay, so for 4 marks, what is it that we need to take note of? We'd say Q lost is equals to 220 grams of water, and then Q gained, the heat that is gained by unknown mass of water. All right, and then we break it down to say what is then the Q, okay, of this 220 grams of water, and therefore what is the heat that is gained by the unknown mass of water. Okay, looking at the temperature before and the after. Okay, so remember the side, it is unknown, and this side we know that it is 220. So because now it is 220 grams and we don't use the 220 grams, okay, so we convert it to what? To 0.22. Okay, this is the specific heat capacity for water, okay, as 4,200, and then we have 57. Okay, looking at the degrees before and after. Okay, so that's basically being got by saying what? 90 degrees minus what? Minus 33 degrees, which is going to give us 57 degrees Celsius. Okay, and then on the other side, what is it that we know about this unknown mass of water? We know that we cannot tell the mass. Okay, remember before we could tell because it was 220 grams, which is converted into what? Into kilogram. All right, and then 4,200 is the specific heat capacity for water, and then we've got 22, which is just finding the difference between now what? There's 33 as well as 10 degrees. Remember, if you say 33 degrees Celsius minus 10 degrees Celsius is going to give us 23 degrees Celsius, because now we're talking about this unknown on this side, unknown mass of water, and then on this side we were talking about the known one, the 220 gram at 90 degrees. So you're comparing the final temperature with the initial one, the final temperature with the initial one. Okay, so this 33 degrees is the final. Okay, the final, because they even stated the final temperature of the mixture is 33 degrees Celsius. However, initially, what was it? What was the temperature for both water? So the one that is 220, it was 90. So that is why we said 90 minus 33. Okay, and the second one was 10 degrees Celsius. So that is why we say 33 minus 10 degrees Celsius, which is 23. Okay, after that we just do our math and we'll make the mass, which is m, it should be in kilogram, the subject of the formula, so that we find it as what, as 545,22 gram, or you can even do it in as what, as kilogram, which is 0.545217 kilogram. Okay, 7.5, they're saying pieces of warm copper, mass of 100 gram at a temperature of 81 degrees Celsius is added to a 200 gram of water at a temperature of 15 degrees Celsius. Okay, so now they say the highest final temperature is 18 degrees Celsius, which is, this part is very, very important because we do it similar to the one that we just did. They say calculate the specific heat capacity of copper. Okay, so that means that copper was not given into that table for specific heat capacities of different matter. Okay, so we do the same thing. We look at the heat that is giving out, which is equal to the heat that is giving in, because this is a conservation of what? The law of what? Conservation of heat. All right, so, and then we have CK, we get MK, delta TK. So we're going to have to look at before, or rather the heat that is given out, which is equal to the heat that is giving in. Okay, so we substitute, because now this 0.1, it was that 100 gram. Okay, but now we had to do a conversion of it to put it in what? In kilograms. Okay, and then now we had to say, okay, we had 81 degrees. The temperature of that pieces of warm copper had a temperature of 81 degrees that is added, okay, to the water of what? Of 15 degrees. So afterwards, therefore, we had what? We had final heat temperature, or rather final temperature is what? Is 18 degrees. So I have to say 81 degrees and subtract it from what? From that 18 degrees, okay, which is the final temperature, just like we did, and we get a 63, which is what we have over here, and then we have 4,200, okay, which is specific heat capacity for water. Okay, because now on the first statement they say the pieces of warm copper of mass of 100 gram at a temperature of 81 is added to what? 200 gram of water at temperature of what? Water at temperature of what? Of 15 degrees. So hence here, over here, we have a specific heat capacity of what? Of water. Okay, 0.2 is a conversion of a 200 gram, but now in kilograms, and then we had to do the difference in temperature, which gives us what? Which gives us 3, and that 3 comes from, we had to say 15 degrees Celsius minus, sorry, not to say 18. Let me just convert this to 18 minus 15 degrees Celsius, which gave us 3 degrees Celsius. Have we substituted the 3 degrees Celsius? Okay, so we do our math, and then we are able to get a 400 joule kilogram Kelvin, which is the specific heat capacity for copper. Okay, so please, most of the time people get that wrong in terms of doing your conversions or doing the difference in temperature, looking at the initial reading of the temperature as compared to the final reading of the temperature, and being able to use that in the calculation, other than using the original temperature, for example 81 degrees. So there was no need for us to use 81 degrees, because now we had to look at the difference. Okay, what happened before, what happened after, so that we can tell the heat transfer that took place. Okay, I want to end today's lesson by a quote from Edward Young. He said, procrastination is the thief of time. Procrastination is the thief of time. So as soon as you start saying, okay, I'll do it tomorrow, I still have time, therefore you are just wasting your time. Soon before you know it, there's not going to be any time left for you to do anything. Okay, so please start preparing for your exams now. Prepare it in style, make it fun, collect all your notes, do your calculations while you still can, because you don't know what will happen on the when you don't have time at all. Please, this is by Edward Young, and I love it so much. Procrastination is the thief of time. Couldn't have said it better. Okay, Anyway, thank you so much for joining us for today's session. I hope you had a lovely time, and I hope we able to tick in your objectives that, okay, I know this, I know this, I know this, I know this, and good luck to your exams. Bye bye.